So the topic for today is LP duality. An extremely important aspect of linear programs and something that we will see. This concept is going to appear over and over again as we discuss algorithms that use LPs. So, unlike most standard descriptions of duality that use what is called the standard form, I would like to show you more gory detail and actually give you the general form of an LP so that you really understand what's happening in duality. So let's look at the specific problem we were looking at, which was, let's say we're maximizing C transpose X, where X are variables. And so here's our constraint matrix. Our constraint matrix is A. So remember that our constraint matrix is A. And we have, A is going to be an M cross N matrix. And so we have this AX, typically saying AX is less than or equal to B. But what I want to do is to show a more general form. So let me say that, okay, so here is maybe, this is X. I'm going to split this into two parts. So here is B. And let's say that the top are inequalities and the bottom are equalities. Okay? So I'll just say maybe the first k constraints, and this is the remaining n minus k. And furthermore, I'm going to split this as follows. So this is a matrix here again. And I'm going to refer to this part as, I'll just call it X prime and X double prime. And we have X prime is greater than or equal to 0. X double prime is what's called unconstrained. Now, of course, it doesn't mean that X prime, double prime, has no constraints within, but it just means that in the linear program, the constraints that are satisfied are X prime is greater than 0. Okay? So, any questions about that? Here's your matrix.
Could you explain X prime and X double prime again?
So, X double, all the variables in X prime are greater than or equal to 0. That's the LP. So, the LP is written as follows, right? So, we said max C transpose X. And I'll just say that I'll call it A inequality times X is less than B inequality. A equality times X is equal to B equality. So I'm just going to sort of stop that sound. Give me a second. Yeah, all right, sorry about that. And X prime is greater than 0. So this is your LP, where A inequality refers to the upper portion. So this is what I call A inequality, and the lower portion I'm just calling A equality. That's just a constraint matrix, right? So in general, you can break up your constraints as to inequalities, and you can always flip them so that the inequalities are always, AX is less than or equal to something. The second part of the matrix, these are equality constraints, and some subset of the variables have to be greater than or equal to 0. This is the general form of any linear program. And instead of maximization, you can have a minimization. But let's look at this one. Okay? Does that make sense? Any questions about that? Okay. So, this is our linear program. I broke it up as follows. Now, what is the dual? So the point of the dual is, can we upper bound the objective? Can we upper bound the objective by taking a linear combination of the constraints? That's what the dual is asking. So you would like to upper bound what the objective can be, C transpose X. And we're going to do that by taking a linear combination of constraints, just like we did it in Farkas lemma. So in Farkas lemma, you took a linear combination of the constraints to assert that a particular linear program is or linear system is infeasible. And here, we're going to use it to upper bound the objective. So how is that going to happen? So what does a linear combination of constraints means? This is written as Y transpose A. So why is that? I mean, you can think of, you're going to multiply the first constraint by Y1, then you're going to multiply the second constraint by Y2, so on and so forth. And that is the same, that has the same effect of doing Y transpose A, right? Because you can think of Y transpose is just going to be a pro-vector, right? Multiplying Y1 and Y2, if this is Y and you want to multiply sort of column, each row by one of the coordinates, that's Y transpose A. So what do we want? Suppose there exists a Y, and this is a Y that's going to be in Rm, right? Because it's the number of constraints. The dimensionality of Y is the number of constraints. You're taking the linear combination. Suppose there existed a Y such that for all feasible X in Rn, suppose the following was true. Y transpose Ax is greater than or equal to C transpose X. Suppose you had such a Y. Suppose you had such a Y. Then what can you say? And just think of it as, let's think of the simpler, let's think of, suppose you had the standard form. So where you know that Ax is essentially less than or equal to B. Suppose this was true. Then, because since X is feasible, Y transpose Ax, you're going to say is at most Y transpose B, because Ax is at most B. Now you have to be careful to make sure that these inequalities actually hold. I'm being sort of loose here, and I'll show you exactly how to make it hold. Since X is feasible, Y transpose Ax is at most B, Y transpose B. So C transpose X, which is the objective, is at most Y transpose B. So this is an upper bound. This is an upper bound on the objective. So you need to find a Y such that this holds. And this program is in effect called the dual. This is like the feasible set of the dual. So any Y for which this holds, we can think of as a feasible Y. This is our aim. And then what we can say is we can try to choose a feasible Y that minimizes Y transpose B. And we'll get the best possible upper bound that we can get. And that is what the dual is. And theory of and LP duality says actually this best possible upper bound is the objective. So that minimum will be this maximum. I should say for all X. Okay, does this make sense? Any questions before now I'm going to basically get into the math.
I just wanted to, what are the constraints of this dual explicitly? Is it just the CTX less than or equal to
This is what you
Y
want.
transpose?
That's all you want.
Okay.
You want this to hold for all feasible X. That's it. Okay? Any questions? Alright, so let's now get into the math. So I'm going to write out this matrix again. So this is A. This is your constraint matrix. What we're going to do is we're going to multiply each constraint by a new variable, a dual variable. So this is y1, y2 up to yn. Remember, this is sort of less than equal to, and this is the equal to. Right? Here's b over here. And I'm just going to, for convenience, I'm going to write c up here. C is just a vector. Remember, the dimensionality of C is exactly n. Okay? So x is somewhere here, right? There's some x over there. Now, this part is going to be, I'll call x prime, which is greater than 0. And this is x double prime, which is unconstrained. So x double prime can be negative anything. So what do we want? We want C transpose x to be at most y transpose A of x. What is C transpose x? So let's write that out. That is Ci xi, I going from 1 to n. Right? And we want this to be at most, so I'm going to sort of write this out now. So what is y transpose Ax? So let's kind of break that up into a sum from going from 1 to n. You are looking at yi. You're looking at basically the dot product. If you open this up, so and you sum this up, you're looking at the dot product of the y vector with a column vector. And then you multiply that with x. So I'm just going to write this out, and you'll see what I'm saying here. I'll say it's y transpose A star I. That's the ith column. And this is A star I times xi. This is what you want to hold. And this needs to hold for all feasible x. By for all, I mean, I should say for all feasible x. Does this make sense? Any questions? This is what we would like to hold. Okay? Alright, so note that the way I could get this to hold is just by looking at the coefficients and ensuring that they satisfy a particular property. So if xi is non-negative, so xi is one of these constraints here. Because xi is non-negative, it suffices to just ensure that ci is at most y transpose A star I. And else, I want ci to be equal to y transpose A star I. Now this is sufficient for the above to hold, meaning that if xi is greater than 0, it's enough for me to just get y such that y transpose A star I is greater than or equal to ci. But if I don't know whether xi is greater than 0 or not, I just want to be really safe, and I'm just going to make them equal.
That's the x double prime case, right?
That is the x double prime case, exactly. This is the x double prime case. Okay? This is what I need. This is precisely what I need. So, this is now a linear program itself. There's no x involved in here anymore. It's actually the I is just the constraint. So let me just write this out separately. I'll show you this picture. The reason why I write it this way is I think of it as you take a column, you take the dot product. In the prime side, you just want that to be greater than or equal to the coordinate. In the double prime side, you want this to be equal to the coordinate. And here you just want greater than equal to. So I'm just going to write this out formally. Okay? So I will say that for convenience, let's just say that x prime is equal to x1, x2. I'm just numbering the coordinates up to, let me say it's x xn, maybe n is a bad number, xp. Okay? P I'm thinking of positive, although it's technically non-negative, and then x double prime is basically xp plus 1 up to xn. Right? I'm just breaking it up as these are the non-negative ones, and these is everything else. So the dual program, right? You have a variable yi for the ith constraint. You have a variable yi for the ith constraint. And what you have is, you'll have if I is between 1 to p, then C of I should be less than y transpose A star I. And if I goes from p plus 1 to n, then C of I is equal to y transpose A star I. This is the basic program. Now, if we have this holding, then we know that for all feasible x, C transpose x is less than or equal to y transpose Ax. Okay? Okay, now we're not done yet. There's one additional thing that we need to consider here. And that is the fact that some of these constraints are inequalities, some of them are equalities. And we're taking a linear combination of these. So remember that I said that this was K. Now think of what you want. I'm just going to write this off on the side. We want y transpose Ax to be at most y transpose B, and that will then complete this bound that we can get. But you have to be careful, like, I'm just writing this, so this is y, and Ax is also some column vector, and you want this to be at most y times this column vector B. We're taking dot products here. But to ensure things coordinate by coordinate, note that one way to think about it is you're multiplying an equation by a variable. If you're multiplying an inequality, you can only multiply it by a non-negative variable. Because if you multiply it by something negative, you'll switch the signs here. Whereas for the equality constraints, you don't care. You can multiply that constraint by anything. So to ensure that y transpose Ax is at most y transpose B, we are going to introduce an additional constraint. And I'm going to put that constraint in here. Just going to write this out over here. I'm going to say for j going from 1 to k, yj is strictly greater than 0. That's just saying that if I look at these constraints here, I want to multiply it by something non-negative. And that's what this is doing. For the others, it's unconstrained. This gives you the entire feasibility of the dual. And so this is the dual here. The dual is another linear program. where the y's are the variables. B doesn't appear here, but C appears here. So let me just write out the statement of weak duality. That if y is dual feasible, then for all x primal feasible, so primal is the original program, right? Primal was the original program. So for all x that are primal feasible, C transpose X is at most Y transpose B. This is our main theorem. So I'll go ahead and prove this. And the proof is actually, it's fairly straightforward. It's just going to be some manipulations of whatever you've seen so far. So let's write the proof out. So we'll say, okay, C transpose X is equal to summation Ci Xi, I going from 1 to n. And we can say that this I can split up as I going from 1 to p, Ci Xi, plus summation of I going from p plus 1 to n of Ci Xi. Now remember, by the dual, so we know that for Xi, I less than p, Xi is greater than 0. Right? This is basically because this is primal feasible. I mean, that's precisely what we defined P to be. We defined P to be the non-negative part. And so for I less than P, Xi is greater than 0. So let's go over here. So we can basically upper bound using the primal constraints. We can say this is Y transpose A star I times Xi plus, now for the negative, for the other parts, we actually have equality. Ci is actually equal to this. So we can simply write that out. I going from p plus 1 to n of Y transpose A star I Xi. Okay, so we've done this upper bounding here. And then we can combine this together. And so now we have I is going from 1 to n of Y transpose A star I Xi, which is really just a fancy way of saying Y transpose Ax. Right? So I'm able to upper bound by Y transpose Ax, which is the same thing as Y transpose Ax. Now I'm going to sort of split this out differently. So what I've proven is C transpose X is at most Y transpose Ax. And now I'll write Y transpose Ax. Now I'll write it over J instead. I'll write this summing over J from 1 to M. I'll say this is Yj times Aj star Xj. Okay, what does this mean? I'm just saying that when I have, when I have a product of this form. Okay, so maybe I'll draw some pictures here. So this is A, this is X, and this is Y transpose. This is Y transpose A X. So I can also write this as saying that I multiply this with any one of the rows, and then I multiply that by the corresponding coordinate here. So this is just taking a linear combination of these. Remember, A transpose X is going to be a column vector, right? And then this is going to be a dot product. So just by writing this sum differently, I get this as follows. Now this I have to be careful, so I'm going to split this up and say that, well, this is J going from 1 to K of Yj Aj star Xj, right? That's saying Aj star is the row, plus summation of J going from K plus 1 to M of Yj Aj star Xj, just breaking this up. Now, why did I break it up as follows? I want to upper bound aj star xj by bj. But I can only do this upper bound if yj is non-negative. In the equality case, I don't care whether it's non-negative or not. And so this is non-negative. This is again by the dual feasibility conditions. And because this is non-negative, I can replace this as j is 1 to k of yj times bj. Right? Because by primal feasibility, that's just the primal. The primal says that aj star xj is at most bj. That's the primal constraint. Plus the summation of j going from k plus 1 to m of yj bj. Right? And this is just the primal. Remember, these are actually equal. aj star xj is equal to bj. Maybe I'll show you the picture again. This picture is a bit to parse, but if you're looking at this constraint, this is an inequality. You're looking at this constraint here, that is an equality. Right? So that's where this is the x double prime part, and this is the x prime part. And so I have an inequality here, so I need yj to be non-negative. In this part, I have equality. It's okay if I can have xj to be unconstrained. And this is exactly y transpose b. So that completes the proof of weak duality. Any questions? Any questions about this? Please ask me any questions about the dual, because we're going to be taking lots of duals now in the next few lectures. And we're going to keep switching between the primal and dual, these viewpoints. So it's very important that you understand what the dual is doing. Understanding the proof of weak duality. Yes? I'll pause here and take any questions that you have. There was a question in the beginning about why certain things are chosen to be non-negative. Please ask me if you want clarifications on that.
Could you repeat the last part where the right sides are equal?
These two are equal?
Yeah.
Yeah. So, like aj star xj. What is aj star xj? It's basically just looking at the jth constraint in the primal, right? Because you're looking at a column vector, you're looking at a row vector here, dot product with x. So this is basically a primal constraint. Now the primal constraints are of two kinds. There are inequalities and equalities. And so what I've done is I have split this out. I'm sorry, let me just get this. Yeah. So I've split this out into the inequality constraints and the equality constraints. And I'm treating them separately because I want to do an upper bound. If I didn't have this part, then it's just equal. So this is trivial. But now it's not so trivial because aj star xj, which is the dot product of the jth row with x. I'm sorry, this is badly written on my part. I don't mean xj here, so there's no j, sorry. It's just a dot product. It's just aj star times x. Right? It's this row times dot product with x. Right? And that's just at most bi, or bj in this case, sorry, bj, right? So what we know is that if you take the jth row, dot product with x, that's basically the jth constraint of the primal. And for the first k parts, that's an inequality. For the next m minus k, it's an equality. And the equality, you can just say aj star x is equal to bj. And so the y doesn't even
follows
matter.
from like the feasibility of x?
It follows from the, exactly, this is primal feasibility. Okay. This is primal feasibility. This is primal feasible. Most proofs you will see of weak duality are much smaller because they deal with what is called a standard form. And in the standard form, instead of having these 4 submatrices, you only have one of them. And you can always reduce the general case to this case, but I think it's important to see the general case. So there are really 4 portions of this matrix: equality, inequality, non-negative, unconstrained. So I'm going to draw another mnemonic picture for you. But any questions about this? So this is weak duality. This says if U is dual feasible, then for all primal feasible, C transpose X is at most Y transpose B. So this gives an upper bound on the primal. Okay, so now what is natural is you have this dual feasible. So which is the best point that you want to choose in the dual? What point should you choose to get the best possible upper bound? Simple answer here, right? So you know that for any Y, weak duality holds. How would you choose? What is the best Y you want to choose? The one that maximizes this, minimizes this, what?
Is it good if P is minimized?
P, which is, you mean, P is just like an index.
Well, I was wondering maybe if like P is minimized, then we're going to be maximizing the equality side of it.
But you cannot change what P is. P is basically what you got from the primal, right? You have some variables being non-negative and some being unconstrained in the primal. So you have no flexibility. Here you're trying to pick a Y. And so what you want to do is you want to actually choose Y to minimize Y transpose B. So I'll draw this out again. Here's the primal. Is maximize C transpose X with, this is A, and this was X. So AX, that's less than equal to, that's equality of B. And we have X prime greater than 0 and X double prime unconstrained. So I'll just leave that. The dual will minimize will minimize Y transpose B. Will minimize Y transpose B. And the constraints are, the way to think of it is, so firstly I'll write down, so remember that this I called P, and this is what remains, and this I called K. So we have for J less than K, Yj is greater than 0. So for these constraints here, you have a non-negativity constraint. And then you have for I less than P, Ci is at most Y transpose A star I, and for I strictly greater than P, Ci is equal to Y transpose A star I. This is the dual. So what you have is equality constraint is, or I should say inequality constraint gives you a non-negative variable. Equality constraint is basically what's called unconstrained variable. And again, like the non-negative variable here, the non-negative variable basically gives you the inequality constraint here. I'll write out the other one, and then I'll say that unconstrained variable gives you an equality constraint. So the primal is a linear program, the dual is a linear program. And just to write this out in gory detail, weak duality just says that the max of C transpose X is at most the min of Y transpose B, and strong duality. So weak duality is easy to prove, and I just proved it. Strong duality requires more effort, it requires using the Farkas lemma, but actually it turns out that remarkably these are equal. And this is sort of a fundamental fact in optimization, that the dual not only gives you an upper bound, but the best possible upper bound is the objective. So maximizing the primal and minimizing the dual are equivalent. Okay? This is duality. Okay, any questions? All right. Now the next.
Kind of.
Yes.
Could I ask a
Go ahead.
question?
Go ahead. Yes. Yes, please. Please
I'm
ask
curious.
questions.
If you take the dual of a dual,
Good question.
what happens?
The dual of the dual is the primal. I was going to put that down as an exercise.
Is there kind of like any intuition behind why?
The dual of the dual is the primal. I mean, essentially, you are reversing all the inequalities that we did. Everything that we wrote, you're just going to reverse it. Because how are you going to take the dual? You're going to multiply everything by every constraint by a variable. So note that there is an equivalence between constraints here and variables here. And variables here and constraints here. If you just write this out, like if you say, okay, how are you going to consider a dual variable. So you're going to multiply each of these by xi. Right? You're going to multiply each of these by xi. And because these are inequalities, you want the first p of them to be non-negative. That's exactly what you get. So you get the non-negativity constraint. And then for the first k variables, you have a non-negativity constraint, and that non-negativity constraint here will give you an inequality constraint here. The remaining will give you an equality constraint, which give you the rest of the matrix. If you mechanically do it, you will recover the primal. It's a good exercise. You just mechanically do it and you will recover the primal. The intuition behind it, again, is that what you have is you have a variable for every constraint and a constraint for every variable. But I could just reverse this, right? This is why I drew this picture here. So every constraint gives you a particular kind of variable. Note that if I flip this picture, I get the same thing. Non-negative variable is inequality constraint. Unconstrained variable is an equality constraint, which is exactly this picture here. Does that make sense? So like this equivalence is the same.
Gotcha, okay.
Questions? All right. Now we'll move to another very important aspect of linear programming duality, and it's something called complementary slackness. Okay, what does complementary slackness say? It says, look at the proof of weak duality when we consider the optima So usually they use stars for the optima. I'm not going to use star because I've used star to index the matrix as well. So I'm going to use hats. When we use the optima, x hat and y hat. So this is the primal optimum and the dual optimum. So when you consider the proof of weak duality, okay, so I just stated weak duality here. But suppose you chose the optima of the primal and the dual, then what happens? What happens to this inequality if I actually chose these to be the optimum of the primal and the dual I defined?
They're equal, right?
They're equal, exactly. They're equal, right? So if x was x hat and y was y hat, these should be equal. Which means that anytime you cannot have a strict inequality in any of these scenarios. You cannot have a strict inequality. Which means that if you ever have if you go through this, when could you have a strict inequality here? If y transpose A star I was strictly greater than Ci, then you would have a strict inequality unless xi was 0. Right? So if y transpose A star I was strictly greater than Ci, then xi must be 0. And analogously, what you get over here is that if aj star x was strictly less than bj, then yj must be 0. So I'll write this out I'll write it out sort of informally here and then tell you. It says that if any inequality in the primal was strict, the corresponding dual variable is 0. And you can always flip primal and dual in each of these. So if any inequality in the dual was strict, then the corresponding primal variable is 0. So I'll write this out more formally over here. I'll just say that so remember that you have these constraints here. So if this constraint was actually strict, this inequality was strict for y hat, which is the optimum y, then actually the dual variable the primal variable there is 0. And if one of these inequalities was strict, then the dual variable is going to be 0. So let me just write that down. That if Cj, I think I used I, so if Ci was strictly less than y hat transpose A star I, then x hat I is 0. And if I think I should be j, if aj star x was strictly less than bj, then yj hat is 0. So if any constraint was not tight, then the dual variable is 0. These are called the complementary slackness constraints. So again, going back to the picture here, it says plug in the primal and the dual, the optimum. Look at the optimum. So the optimum is going to satisfy all of these constraints, but some of these constraints may be strict inequalities. If any inequality here is strict, then the corresponding primal variable is 0. And if any inequality here is strict, which is for the first part, if there's any inequality which was strict, then the corresponding dual variable is actually 0. And you prove it by going through the complementary slackness proof. Okay, does that make sense? The notion of complementary slackness, it says that when one of the constraints is actually not tight for the optimum, then the dual optimum actually has a zero variable there. So in some sense, the non-zeros, the non-zeros of the dual actually give you the tight primal constraints, the non-zero variables. Questions?
To prove this, would you do a proof by contradiction, or?
You could just, so let me state a theorem and then I'll tell you how to prove it. You could prove this directly by walking through the proof of weak duality.
Okay.
You would walk through the proof of weak duality. So what you would do is you would say, let me go through the proof of weak duality and ensure that anytime there's an inequality, it's actually an equality. Because I know that this finally has to be equal. And you'll see that whenever Ci is strictly less than y transpose A star I, then Xi has to be 0. And then you could also do a proof by contradiction there, right? You say if Xi was non-zero, then you would actually get a strict inequality. So let me state the complementary slackness theorem. And this is called the complementary slackness. It's suppose instead of hats I'm going to use tilde. Suppose x tilde is primal feasible and y tilde is dual feasible. Then x tilde, y tilde are optima if and only if x tilde and y tilde satisfy the complementary slackness constraints, slackness conditions. So it's tighter. What it remarkably says is that if you have two feasible points, if you had two feasible points that satisfy these constraints, then those feasible points actually are the optima. And we are going to use this very heavily in some algorithms we're going to come up with. But complementary slackness says that now to understand, like if you had a primal feasible point and you were asked, is this actually optimal? Like how do you know? Maybe there's a better primal feasible point. But there is a certificate that if you get a dual feasible point and they both satisfy complementary slackness, then you know that they're actually mutual, then they're both the optimal. The proof is basically walk through the weak duality proof and show that every inequality is actually an equality. Right? And if in weak duality, if they're all equalities, right? If you get equality in the weak duality, then you know that they're actually the optima. Then you actually, because you know that those are the best possible points. Those are the optima. Okay, any questions about this? This is quite a bit, so you do have to go back and read through this, but duality and complementary slackness are going to appear many, many times in the course of this course, and also they are very fundamental concepts in optimization. Please ask me questions at this point if you to get more intuition or whatever. I'm happy to sort of pause here and take any questions you have. So I'll just pause the recording and take any questions that may come up. To get some intuition, let's look at the dual of a very simple linear program, shortest path linear program. So here's the primal for ST shortest path. Now I showed this in the previous lecture, and so we maximize dt subject to the distance of S to itself is 0, and for all edges of arcs uv, the distance to v is at most the distance to u plus the weight of uv. Right? And remember, the variables are dv. So I have a variable for each. That was the shortest path distance. Okay? For the dual, okay, I have a variable for every constraint. So what variable do I have here? I have a variable ye, or yuv. I'll call it yuv. That's the variable I have here, yuv. Is yuv going to be non-negative, unconstrained, what? And let me just call this one variable. I have one extra variable z. So what happens is yv unconstrained, or is it non-negative? Yes? Someone? Anyone? So yuv is non-negative because it's an inequality constraint. The z is unconstrained. Okay, so I'm just going to put that down there. Okay, now what are the constraints going to be? So the two vertices S and T have a special role, so I'm not going to deal with them for now. So I'll just write that firstly for all v not equal to S or T. So I have a constraint for every variable. So consider the variable dv, and I'll get a constraint corresponding to dv. I'll get a constraint corresponding to dv. That constraint, I get a constraint by looking at the coefficient of dv in all constraints and the objective. Okay, so if dv is not equal to st, what is the coefficient? What is the coefficient in the objective? What is the coefficient of dv in the objective?
0.
0. How many, okay, now this, how many constraints does dv appear in? How many constraints does dv appear in?
Should be equals to the number of its neighbors.
The number of its neighbors, right? So let's look at v. Now note that it's different whether it's an in edge or an out edge. So you have in edges and you have out edges. You have in edges and you have out edges. So for each edge, v appears in one of the constraints. For this edge, it's plus dv. In these edges, it appears with a, okay, so let me rewrite this constraint. I'll say it's dv du minus du is equal to this weight, right? This is the way I should write the constraint. So note that when it's an in edge, it appears as plus dv. When it's an out edge, it appears as minus dv. So if you look at what this constraint is, you put together all the constraints, and you get the following. You get the sum. So for every edge that is an in edge, dv appears with a plus 1. Where every edge where it's an out edge, it appears as a minus. So for every I'll say u in the in neighborhood of v. For every u in the in neighborhood of v, it appears with a plus. So it's like I'm multiplying each of those constraints by yuv. I get yuv with a plus, with a positive coefficient, minus the summation of w in the out neighborhood of yv w. And this is going to be equal to 0. Because remember, we said this is going to be equal to whatever coefficient you get. Now, if you look at t, t is going to behave differently. T is going to behave differently because t has a coefficient of 1. So if I write this, I'll get a similar constraint with t, except there the coefficient is going to be 1. So I get the summation of u in the in neighborhood of t, u t, minus the summation of, say, w in the out neighborhood of y t w. And this is going to be equal to 1. This is going to be equal to 1. Okay, and it's a bit messy, I'm sitting over there. Then finally, let us look at the variable ds. Now ds has a coefficient of 0, but ds appears in the special constraint with z. And otherwise everything looks exactly the same, but it's going to appear with this as well. And so what you get is the summation of u in the in neighborhood of s, yus, minus w in the out neighborhood of t, s, ysw, plus 1 is equal to 0. Right? Because I get a plus 1 from the ds. I look at ds everywhere. Okay? And now I'm going to minimize something here. And I'm going to minimize the summation basically over all edges of ye times the weight. So I'm just going to call this, the weight of e. What is that constraint over here? What does this look like?
Flow conservation?
It's flow conservation. That's flow conservation for everywhere other than S and T. What does that mean? That's the net flow that is going into T. That is the net flow going into T. So 1 unit of flow going into T. This is the net flow going into S, and it's saying it's minus 1, which means that 1 unit of flow is going out of S. And what are you trying to minimize here? What are you minimizing?
You're minimizing the total number of edges you would use?
It's like the cost. Suppose the cost of an edge is the weight. Like you have a weight. So the cost of the edge, that's how much you have to pay for using that edge. And you multiply it with the amount of flow that you're sending. So you're sending 1 unit of flow from S to T. You don't have capacity constraints. What you actually have is a cost constraint. Does that make sense? sorry, I'm just going to zoom out a bit. This should be really surprising. You start with shortest path, and what you have over here is like min cost flow. So the dual of shortest path is actually min cost flow, or min cost ST flow. So let me just, any questions at this point? It's hard to see your faces, but you should blow your mind away. If you haven't seen this before, like, this is amazing. What LP duality says is that there's some connection between shortest paths and flows. How do you solve this? Okay, so just verbally tell me, what is the solution for this min cost flow problem? What is the solution for this problem?
For all the edges on the shortest path, YE would be 1 and the rest would be 0?
Okay, good, exactly. So you can route one unit of flow along the shortest path.
Right.
So the dual solution is the shortest path and the primal solution is the distance. The primal is just giving you the distance. The dual gives you the shortest path. So indeed, the dual here, just to write this down, dual is route one unit of flow from S to T with the weights being like cost per flow. It's like the cost per unit of flow that you use. The dual solution is the shortest path, is a shortest path, or is technically a combination of shortest paths. So if there are multiple shortest paths, the dual could choose to send a flow along all those shortest paths. But note that there is this correspondence between the paths and the flow, and the shortest path distance and the min cost flow. And this is going to reappear again when we study min cost flows. And just to sort of make this completely, to see this again, let's look at what complementary slackness says. Now in the primal, in the dual, all the constraints are equality constraints. So there's really no point in looking at complementary slackness with respect to slackness here. There is no slackness here. But there's slackness over here. So what this says is if a constraint is not tight, then the dual variable is going to be 0. What does it mean for that to be not tight? So in complementary slackness, it says that if dV, this is, let's say, the optimum, right? So d hat is strictly less than this weight, then y hat uv is 0. What does this mean? It means something that's actually fairly obvious in terms of shortest paths. Anyone hazard something? All right, I will basically, if dV is strictly less than du plus wuv, then the edge uv cannot be on a shortest path. Because the definition of a shortest path is this constraint has to be tight. So this is simply saying that these are just two equivalent ways of saying that the edge uv is not on a shortest path. Right? Because for all edges on a shortest path, if you look at a shortest path, then obviously the shortest path from S to here from S to V is equal to the shortest path from S to U plus the weight of that, which would be the right-hand side here. So the fact that it's a strict inequality means that UV cannot participate on the shortest path. So that's what complementary slackness says. Okay, any questions about this? So the primal for the ST path, ST shortest path, the dual is basically a min-cost flow between S and T. Between S and T. Questions? All right. Let us now go and look at flows. And let's write out the primal for now our capacitated flow and look at the dual. So in this case, I'm probably just going to write out the dual, and I can answer quick questions on it, but I would leave, work it out yourself as if you have specific doubts. So this is for max flow. This is for max flow. So what are you maximizing? You're maximizing U in the out neighborhood of S. I mean, I think I've flipped the picture here. Let me see if... Well, let me go with this and we'll see what happens. So X SU, this is the total amount going out of S minus let's say W in minus of S, X WS. So you maximize the flow, then let me state the flow conservation constraints. So that would just say that for all V not equal to S comma T, write this as yes. Sorry, I'll just use, say W is here and U is there. Doesn't make a difference. So W being in the out neighborhood of X V W minus X UV, for U being in the in neighborhood. Then you have capacity constraints that for all, I'll say edges UV, the capacity, so you have X UV is at most C of UV, and then of course X UV is greater than 0. So this is the primal problem. Let's look at what the dual is. So we have a variable for every constraint. Now we have two kinds of variables. I will refer to these variables as YUV. Those are the dual variables I have here. And the dual variables for these, I'll call them ZV. Because this is an inequality, I will get that YUV is going to be greater than 0, but I'll write this at the end. So what happens in the dual, of course, is now we have a constraint for every variable. And so we have three kinds of edges. We have edges that are incident to S and T, edges that are not incident to S, edges incident to S, edges incident to T, and edges that are incident to neither. And so we get sort of separate constraints for each of those. I'll just walk through one of them and I'll write out the others. So for all edges UV, where we're sort of not equal to S comma T. What I mean is that neither U nor V is part of S comma T. So you're looking at some edge and looking at it as UV. So where does the variable xuv appear? Well, it definitely appears over here. And so it definitely appears over here, and it has no coefficient up here. So it appears in this constraint with a coefficient of 1, and then it appears in these constraints with two possible, in two constraints, the constraint for u and the constraint for v. And because, let me just make sure I'm getting this right, because all the variables are non-negative, I'll get an inequality constraint. All the variables are non-negative, I get an inequality constraint. So if I write this out, what I will get is actually yuv plus zu minus zv is greater than or equal to 0. Right? Because if I look at xuv, it appears once over here with a yuv, and it appears once with a plus sign and once with a minus sign. I get plus for the u and minus for the v. Okay? And that's what I get for all edges of this form. So for all edges SV, I get YSV minus ZV is greater than 1, and I get the 1 over here because of the coefficient over here for every edge of the form SV, and then for all edges, maybe I should call this SW, just so that I use the SW over here. For all edges of the form US, I'll get YUS plus ZU is greater than -1, and I get a -1 because it appears with a minus sign over there. And then for all edges, so basically it's a bit mechanical, one has to sort of sit down and write this, but once you write this you will see what's going on here. So for all edges TW, you get YTW minus ZW is greater than 0. You get a 0 because you have a coefficient of 0. You don't have any ZT because you don't have a flow conservation constraint for S or T. And then for all edges of the form UT, you'll get Y UT plus ZU is greater than 0, okay? And you'll get YUVs are greater than 0. So you get some kind of long thing over here, and what you then get is a minimization because you start minimizing with these coefficients, with these capacity values here, you'll get YUV, CUV. Okay, so this looks extremely onerous, but I promise you we can make it much simpler. Essentially, every constraint looks like YUV plus ZU minus ZV is greater than 0. And if you rewrite this a bit, you basically get this is ZV less than or equal to ZU plus YUV. Where have you seen a constraint like this? What does this look like?
The shortest path.
It looks exactly like the shortest path constraint. It's a path constraint. And now you can say, but what about these? Well, in some sense, it's just saying that the Z corresponding to S and the Z corresponding to T is like a fixed quantity. So I'm going to simplify this program by basically setting, let me set ZS to be -1, ZT to be 0, And then I promise that if you were to do the math, you'll get, okay, so I'm just going to write CE times YE. And what you just get is for all edges UV. For every edge UV, you get ZV less than equal to ZU plus Y UV. Right? Basically, you can check that this is the case. And also believe me that you can set this and then just add 1 to all the Z's. It's just going to be convenient because if I add 1, then Zs will become 0 and Zt will become 1. So I get Zs is equal to 0 and Zt is equal to 1. I'm just doing a simple manipulation. You could imagine just adding everything because you're only looking at differences. This is the dual. So the dual is looking kind of like some kind of shortest path like problem, except where there are actually variables that are the weights. The weights themselves are variables. So let's consider any path. Any path from S to T. Okay, and I'll just call it S is equal to V0, V1, V2, all the way up to Vk, which is going to be equal to T. So consider any path. And imagine that you sum up the weights along that path. So I'll just say I going from 0 to k minus 1. I'm just going to sum up all of these weights, Vi, y of Vi plus 1. Now this is by the constraints of the dual. This just says this would be greater than or equal to Z Vi plus 1 minus ZVI. That's a telescoping sum. So this ends up being Zt minus Zs, which is equal to 1. Okay? So what is the problem? What is the dual saying? It says put non-negative weights and those non-negative weights are the y's, so that, I mean, I'm sort of putting this in words to prove this is somewhat this is formal, but so that for all ST paths, the weight of the path is at least 1. I mean, I'm just rephrasing this. Technically, this is not what the dual says. The dual says what's given here. One has to prove an equivalence, but you can imagine that it's effectively that's what it's saying. It's saying that you have to create weights so that the distances have this property. You have to put weights so that the distances from S to T is going to be 1. Alright? And so for those of you who've seen the proof of Maxwell-Min cut, this is actually the cut LP. And we need to prove that the solution is actually going to be the cut. But let me, leave you with the fairly simple, the simpler part is, so I'm just going to let delta S denote the cut, like the edge is going from S to V minus S, right? That's just saying that if you took any cut of the form, this is capital S, then that's these edges going is delta S. And so let's first prove the simpler claim that the min of the dual is at most the min cut, the min ST cut. Why? Because I just need to show you that whenever there is a cut, I'll get a dual feasible point. For every cut, I'm going to get a dual feasible point. And the proof of that is relatively straightforward. So let S subset of V be such that little s is in S, so NT is not in S. So that's just saying that here is S, here is T, and this is some set S. What you can do is, for all edges in delta S, set YE is equal to 1. So this means that YE is the indicator for the cut. And set YE is equal to 1. And if E is not in this set, you just set YE is equal to 0. Now, YE is dual feasible. And so the min is at most the cut value of delta S, which is basically just the sum of all edges in this cut, in this cut of CE, of the capacity. Right? And so I'm just sort of sketching this proof. And so therefore, for all ST cuts S, the min is at most a summation of E in delta S of the cut value, and hence the min. By min I mean the dual min. The min of the dual is at most the min cut. Now what the max flow min cut theorem says is that these are actually equal. So this is the famous max flow min cut theorem. And there are many ways of saying this. The way that I'm going to phrase it over here is that the min of the dual is equal to the min cut, the min ST cut. And of course, by duality, we know this min of the dual is actually the max flow. And this is strong duality. The strong duality proves that the max flow is the min of the dual, but we need to prove that the min of the dual is actually the min ST cut. What we've only shown is that it is at most the min ST cut. And so for this, I'm running out of time. I don't want to cover it in this lecture, but in the next lecture I'll cover a very slick proof of the max flow min cut theorem by Garg, Vazirani, and Yanakakis. And so once we get that, we'll have the max flow min cut theorem. Then I want to discuss what complementary slackness means for flows. And once we do that, we'll move on to min cost flows, where again we'll be seeing the sort of equivalence between shortest paths and flows. So this is a good time for me to end. So I'll stop here and I'll take any questions that you have.